Hello everyone, we are Team 4 for our sophomore design project class, or also Group 39 for Innovation Day. Today we're going to be talking about our project, which is a solar AC motor drive, and it actually has two pieces to it. The first of which is a DC to DC converter, which comes from our initial input of the solar panel, and then it turns into AC with our DC to AC converter, which will be what we will be used to power our AC motor, which in the end we actually want to be able to control the speed of that motor. But we're still in the process of actually building these converters and making sure all the issues are ironed out so that we're ready to go for actual Innovation Day to show you all. Our first step here is actually the solar panel. It takes in the DC voltage, and you can actually see it right here with our charge controller. Right now it's drawing at about 12.9 volts, about 13 volts. So it's a little bit of a 1 volt difference, but for now it's okay as we're just initially testing, and so far it's been working properly. And then this turns off sometimes, but it's working. And then this right here is connected to our battery, which is actually charged by the solar panel, which we will be using for our circuit. And this battery is supposed to be powering this boost converter, which is our first converter, is a DC to DC. It takes our 12 volts solar panel input and goes to around 24 to 22 volts, which is enough to power the rest of our circuits. So what a boost converter needs is you have a MOSFET, a diode, an inductor, some capacitors, and obviously some resistors. And putting all this together, you'll be able to boost your voltage. One of the important factors here are the gate driver though. For the gate pin of the MOSFET, you actually do need something to drive it. And so we've been using as an Arduino, and as we will discuss a little bit later on what code that we actually use to produce a waveform for it. And so our results of the actual boost converter itself, the load is right here, and this is where our the output of our load would be. And if we put an oscilloscope to it, we actually have this result. So as you can see, this is the 0 line, the 0 volts, and it goes all the way up to 22 volts. So it's a very good output, as we started from 12 volts. And the next step, we'll be talking about the Arduino.
Okay, so before we go into our H-bridge, I'm gonna be talking about the middle step, which is our coding for the PWM and our SPWM. So for our boost converter right here, we need a PWM signal that will help drive our MOSFET. Ideally, I created this code right here, which will ideally send a 24% duty cycle to our MOSFET. That way we'll be able to control, drive the circuit and help it boost up to a 24 volt voltage. And then the second part was writing the SPWM code, which will go to both our gate drivers. Ideally, we want a sinusoidal waveform for this, and here on this code, you can see the 4 inputs or 4 output pins that I use were 9, 10, 5, and 6 from our Arduino, which these pins are specific for SPWM. Now that I've been able to talk a little bit about our code and what they are used for, I'm gonna hand it off to my teammate who will talk about the H-bridge.
Okay guys, we are now into the final part of our project, which we're talking about the DC-AC conversion using the H-bridge. The H-bridge is composed of 3 parts, which is the H-bridge, the LC filter, and the LC load. As you can see from our multi-sim schematic over here, we have our 2 gate drivers that previously our teammate Christian talked about. And we will be using the Arduino Uno to power the gate drivers to produce a high and a low end output that will be driven into our MOSFETs. As you can see over here in the oscilloscope, our high end output and our low output are produced here. The high end is a constant DC voltage of around 12 volts, which is similar to the battery, since our battery's max output is 12 volts, as well as the low end of the output, which peaks at 12 volts, but changes duty cycle, which is its function in order to power the MOSFETs. As you can see here in the breadboard, we do have our 2 gate drivers ready and set up. They're pretty similar schematic-wise, nothing changes, but as long as the 2 outputs for each gate driver goes into the MOSFETs correctly configured, we then go into our LC filter, which produces the rectangular signal that we've got from our DC voltage into an AC sinusoidal waveform that we need to power our AC motor drive. And which that is represented by our resistor, which is the LC load. So for Innovation Day, we will replace that resistor with our AC motor drive. And as you can see here in the picture, this is ideally the sinusoidal signal that we want, which shows the DC and AC conversion was a success. As you can see, for Innovation Day, we want to control the speed, but we are having some issues to troubleshoot, and I hope you guys enjoy our presentation. Thank you.